Alright, hey everyone, I'm Avnish, an 18-year-old quantum computing enthusiast, and this is my personal newsletter. So for those of you OG subscribers out there, you'll notice that things look a little different. Well, I decided to switch to doing a video newsletter since that would be a little more engaging for you guys and a little bit more fun for me. We've got a lot to talk about since I haven't done a newsletter in over a year. So without further ado, let's jump right into it.
So first up is the Quantum Open Source Foundation's Mentorship program. So this is an opportunity for QC enthusiasts to dive deeper into the field by working on open source quantum software projects. And they get to work on these projects with a mentor, an expert from industry or academia. This mentorship program is normally for undergraduate or graduate students, but I was lucky enough to be a part of this in high school. To get in, applicants were given 4 screening tasks, and they had to pick one and submit a solution to it within 2 weeks. Mentors would choose which mentees they wanted to work with based on their solutions to the screening tasks. Okay, so the screening task I did was about using the quantum approximate optimization algorithm to solve the max cut problem. So let me just give a quick idea of what the max cut problem is. So we have this undirected graph like this, and we have 2 paintbrushes, a blue paintbrush and a red paintbrush. And our goal is to figure out a way to paint the corners or vertices of this graph such that we maximize the number of connections between nodes of opposite colors. So I've painted my graph, and notice that this edge has a blue and red node that it's connected to. So we would get 1 point for that. Whereas this edge over here has 2 blue nodes, and those are the same color, so we don't give any points for that. And our goal is to maximize our score. An equivalent way of framing the problem is like this. How can I draw a cut through this graph that partitions the nodes into 2 subsets such that the maximum number of edges are cut? And that's why it's called the max cut problem. So what I had to do was build a QAOA circuit to solve this problem by figuring out the best way to paint these nodes of a graph. But there was a twist. Instead of having regular edges like these edges had weights to them. So for example, this edge would have a weight of 5, this one might have a weight of 3, and so on. So that's what the max cut problem is all about. And that's the screening task that I solved to get into the QOSF mentorship program. So I'll leave a link in the description below to the GitHub repository that I submitted with the solution to this problem. And I'll also leave a link to another repository that compares the performance of my code to other techniques, such as using D-Wave's quantum annealers to solve the max cut problem and using a classical computer to solve the max cut problem. During the program, my mentor was Dr. Veselin Guerguev, who introduced me to the whole world of quantum annealing, logistics, and optimization. So, Veselin, if you're watching this, thanks for being such an awesome mentor. I also had 2 teammates, Shantam and Aniket, who were final year undergraduate students from India. They were super supportive and helpful and willing to answer my questions and have meetings with me at times that were inconvenient for them given the time zone difference. So again, thanks Shantam and Aniket. So the project we worked on is related to the vehicle routing problem. The vehicle routing problem is the quintessential logistics problem. So imagine you're a delivery company with a depot, a few trucks, and maybe 30 or 40 customers that you have to visit. Your goal is to find a route for all of these vehicles so that each customer receives their product. And you want to minimize the amount of time the vehicles spend on the road, because the longer they're on the road, the more you have to spend on gas. So this might not seem too complicated, but it's actually quite difficult for computers to solve, since they essentially have to try every possible solution and see which one's the best. The set of possible solutions grows rapidly when you increase the number of nodes or vehicles in your problem instance. So our research was focused on using quantum annealing to find optimal solutions to this problem. Not perfect solutions, but reasonably optimal solutions to VRP instances. After the project ended, Shantam and I joined Dr. Pawel Gora's research group at QWorld, which is also looking into using quantum computing for the vehicle routing problem. So we have people in our research group working on VQE and later VQE for the vehicle routing problem. We have people working on QAOA. And we also have a group that's working on using graph coarsening to simplify the problem so that it's more reasonable to map it onto quantum processors. My division of the group, which includes me, Shantam, and Ashish, is focused on using quantum annealing. So building on our research that we've done in the past. I'm excited to announce that our research group will be presenting a few video-on-demand talks at Warsaw IT Days 2022, which is one of the biggest IT and data science conferences in Poland. So if you're interested, sign up for the conference and check out our presentations. Up next is the Feynman Mafia. So this was an initiative started by my friend David, and the goal of this mafia was to get a deep intuition of math and physics. So the way it's been working so far is that we've been following a series of lectures by Professor Frederick Schuller. One lecture series is the Geometric Anatomy of Theoretical Physics, which covers a ton of cool concepts in differential geometry, from set theory to topology to tensors and differentiable manifolds. And it's pretty cool. This completely changed my perspective on mathematics. And it's a very different way of looking at math from what we're used to in high school. And the other lecture series we're following is the Horace International Winter School on Gravity and Light. And this basically covers the math behind general relativity. And it turns out there's quite a lot of overlap between that and the geometric anatomy of theoretical physics. So yeah, we've been learning using the Feynman technique, and that's basically built around the idea that teaching is the best way to learn. So we go through the lectures on our own beforehand, take notes and study them, and we have sessions each week to explain concepts from those lectures to each other. And when we explain those concepts to each other, we poke holes in each other's understanding and find holes in our understanding. And that helps us fill in those gaps and get a more solid intuition of what we're studying. So that's what we've been doing so far, and it's been pretty cool. So huge shout out to David for starting this whole thing. So January kicked off with MIT's iQuHack. And this was basically a quantum computing hackathon run by MIT. And in this hackathon, I teamed up with Anne May, Samuel, Esteban, and Yilian. So we competed in the QTech division of the challenge, in which we got to work with real quantum hardware being developed by QTech. So we had to choose between either working on some kind of project relating to quantum key distribution or some kind of project relating to quantum error correction. So I have some experience with quantum key distribution, so I didn't really want to do that. So we decided to dive into quantum error correction. Now this was our first time doing this, so we had a lot to learn in only 48 hours. Or actually 24 hours, but we ended up learning a lot. Ultimately, our project didn't end up being very interesting since we placed a ton of constraints on ourselves. We wanted to be able to use an error correction code. We wanted to be able to run it on a useful quantum protocol or algorithm. And we wanted to run it on real quantum hardware, which was very difficult to do or possibly even impossible since we only had access to a processor with up to 5 qubits. And the Shor code, which was the best error correction code we could find with the minimal number of qubits, was, I believe, 9 qubits. It required 9 qubits. There is a way you can make it simpler by resetting the ancillary qubits halfway through the error correction scheme, but we couldn't really do that because QTech's platform doesn't support resetting qubits midway through the computation yet. So we ended up just applying a simple error mitigation technique on the superdense coding protocol, and there's a link to our GitHub of that project in the description below. All right, so that's it for now. Throughout April, I'll continue working on my research into quantum computing's application for vehicle routing. I'll also be working with my research group on articles explaining our research. I'm currently seeking an internship in the QC space or a research project to work on over the summer. So if you know someone who has a position available, please feel free to send this to them. But yeah, that's it for now, and I'll see you guys in April.